the way, I love your is it a dress or a top?
It's a dress. So yeah.
Nice.
So it has a belt that matches the color of the planets. I almost put on my
love it. It's such a nice dress.
Thanks. I'll have to send you the link at some point.
Please.
They do dinosaur dresses as well.
Oh wow, that is so cool. Hello and welcome to Physics Chat. Physics Chat is a show where we talk to real-life researchers at the forefront of their research and learn more about what it's like to be a modern-day physicist. My name is Susanna and I'm back with my amazing co-hosts, Joe and Fox. It's great to see you both, and how are you doing?
I'm really well, thanks, Susanna. How are you, Fox? How are you doing?
Yeah, I'm good. How are you, Susanna?
I'm doing great, thanks. And I'm really looking forward to chatting with our next guest, Dr. Sam Penny, who is a senior lecturer at the University of Portsmouth. She researches galaxy evolution and how low-mass galaxies stop forming stars. Welcome to the show, Sam, and how are you?
I am very well, thank you. And thanks for inviting me to talk to you.
Brilliant. I'm really glad we've got you on, Sam. This show is great for me because we get these really fantastic physicists on and ask them quite basic questions, which helps my understanding quite a lot. So the first thing I want to ask you is, could you explain for us just what a galaxy is in general?
Okay. So this is actually a question we don't have a firm answer to. I'm going to talk a little bit more about that later. But broadly, we can sort of define a galaxy as being a collection of stars and sometimes gas and dust. And we think these are contained in a halo of dark matter. So we can detect the stars, the gas, and the dust with our various telescopes. The dark matter, we just sort of have to infer that it's there based on the behavior of other objects. And we assume that these are all a gravitationally bound object and it's sort of its own self-contained system. And so the stars form, go through their lives and die contained within this thing we call a galaxy, basically. And so these are what I observe and carry out my research with. We think most of these have got a supermassive black hole at the center, though possibly not all of them. And this is an area of debate that I actually study as part of my research as well. Okay.
Do all galaxies look the same, or are there different types?
Every galaxy we look at is going to be slightly different in some way. So no galaxy has the same number of stars as any other galaxy. No galaxy has the same amount of, say, gas or dust and dark matter as another galaxy. They all vary slightly from galaxy to galaxy. So I think it's a bit like sort of humans or animals or similar things. You can sort of say broadly they are all the same sort of, I guess, species, as it were, but each one is an individual. It's all slightly different. So what we do with galaxies is, rather than saying, oh, that's a galaxy, we start dividing them into sort of different sort of subtypes. So some galaxies are elliptical galaxies. They're spherical amalgamations of stars and dark matter. And then we go through to spiral galaxies, which are galaxies such as our own Milky Way, with these beautiful, well-defined spiral arms. They just look fantastic in images. They're the ones that always get shown sort of the flashy images when a new telescope starts showing us its data. We have objects known as irregular galaxies as well. So these don't quite fit the elliptical definition. They don't fit the spiral definition. So we give them their own subtype. And then all of these are further subdivided and so on. And so, yeah, no galaxy is the same. I think that's very important to say. And so even looking at these in detail as astronomers, we can start to pick apart subtle differences, even in two galaxies that look roughly the same, but there's always differences within them. So yeah, they're very interesting objects to study.
So as you said, the spiral galaxies are the kind of the pretty ones that we see all the pictures of. I assume there's a good amount we can learn from all types though. Absolutely. So all types of galaxies give us really important information. Elliptical galaxies tell us a lot about sort of how, so we sort of see these as being sort of what all galaxies will eventually turn into, or okay, that's a bit of a hand-wavy controversial statement to research astronomers. Most very large galaxies are elliptical galaxies. So once you get to a certain size in your galaxies, they all seem to be ellipticals. Spirals, we can really study when new stars are born. They're born in the spiral arms, forming these beautiful, really bright features that we pick up in our images. But these are not actually the most common galaxy type. So we're used to seeing things like our Milky Way, similar galaxies to our Milky Way in pictures. But things like the Milky Way are actually
in terms of just how many galaxies they are actually somewhat unusual. So most people don't know this, but the Milky Way is a parent galaxy to maybe 30, 50, 100 little tiny, what are called dwarf galaxies or low mass galaxies. And these are actually the typical galaxies in the universe. They're not the most exciting things in an image, a sort of fuzzy blob of stars, but those are the typical galaxies. So if we want to really understand how galaxies work, we want to know how a typical galaxy works. It's those little faint things are the ones we actually should be looking at.
So what type of galaxies is it that you study?
So I've just given it away a little bit there. These are low mass galaxies or dwarf galaxies. So whilst a galaxy such as our own Milky Way has maybe a few hundred to a few thousand billion stars in it, these galaxies have up to about 1 billion stars like our sun in them, and down to just a few tens of thousands for the smallest ones of these that we can observe. And so I examine these and I try and work out how we get from these galaxies actively forming stars. So we see a lot of these galaxies actively forming new stars today. So gas clouds collapsing and eventually getting dense enough that new stars can form in those gas clouds. But we also see a lot of those where that process is no longer taking place. And I'm trying to work out what goes on in the middle there. What is stopping that star formation from switching off? We also see some of these that we think are very, very low mass spiral galaxies that just for some reason just gave up on forming stars and formed these galaxies known as dwarf ellipticals. Those spiral arms fade away over time. They get disrupted by interactions with other galaxies. So I'm really trying to work out, how do we form these objects?
Well, that leads nicely on to my random question. So Sam, out of the 7 dwarves in Snow White, which one do you identify with?
Okay, so I think there's actually 2 that I identify with. Sleepy, definitely. Anybody who uses a telescope for their observations or who has to spend a night at a telescope will know that this is one of the most exhausting things you can do. You start at maybe 3 or 4 in the afternoon and might go to 6 or 7 in the morning. You get your calibration observations done and then you observe until the sun comes up, basically. So sleepy, definitely. And then sneezy, because I am incapable of sneezing less than 5 times in a row. It's a bit embarrassing.
Oh, brilliant. What about you, Joe?
I was going to say, I mean, I suffer from hay fever, so it comes around to summer, then it's definitely sneezy.
I think mine would be happy because I'm just quite a bubbly person in general and quite chatty. And what about you, Fox?
Definitely dopey, because I have not had my coffee this morning. But anyway, let's get back to the physics. So we've heard about galaxies and how they form. Could you explain what you're currently researching in more detail?
Yeah, absolutely. We want to know, obviously, how, as I've mentioned earlier, how these low mass galaxies, what processes actually cut off star formation from happening in these galaxies. So at some point in their lives, a number of these galaxies lose the ability to form new stars. There's various theories in galaxy evolution as to what processes cause this. So for high mass galaxies, so really, really big, giant galaxies, we think that heat and basically winds blown off by the supermassive black hole in the center, due to all the complicated physics that goes on there, we think it releases enough energy into the galaxy that it can blow the gas out of these galaxies. So if we think of the galaxy as being sort of a well, or a sort of a bucket that contains all the stars, if it's a really, really deep sort of well or bucket, you need a lot of energy to throw the stars out of it, or throw the gas out of it, I should say. So you need something really, really powerful in the center of a big galaxy. Now, at the lower mass end, we thought it was supernovae that was driving the gas out of them. And we definitely know this happens. This is definitely a valid mechanism for what drives out the gas in low mass galaxies. If there's no gas, there's nothing to collapse into new stars. And so this galaxy ends its star forming life. However, within the last 10 years, we've started observing a number of these low mass dwarf galaxies with the signature of having what is known as an active galactic nucleus. That is a supermassive black hole that is accreting gas. That gas is being heated, and we can detect the signature of that heating in data that we take from telescopes from those galaxies, specifically in spectra from the galaxies. Now, this was thought not to happen in these galaxies. It was thought to be a process that just didn't take place. So what I am researching is, how often do we see these evidence for these supermassive black holes, these accreting supermassive black holes in these galaxies, also known as active galactic nuclei, and what impact do they have on the galaxy? So I map galaxies using spectroscopy, and I look for signatures of the heating throughout the structure of the galaxy. So how far from the center can we actually see this heating taking place? And do galaxies that have this signature of AGN heating, are they any different to those that don't?
Wow, that's really interesting. So what's the biggest mystery in your research currently?
Okay, so this is a problem that influences a huge swathe of astrophysics and cosmology, and this is something called the missing satellite problem. We do not see enough low-mass galaxies to match what is predicted by the theories that cosmologists come up with for how many galaxies there should be of a certain mass. They predict far more dark matter halos in their cosmological models than we observe galaxies. And so what we spend a lot of our time doing is trying to count the number of faint galaxies. And we don't observe enough. And so this is the missing satellite problem, called satellites because these galaxies are typically orbiting bigger galaxies like our own Milky Way, just as satellites orbit the Earth. And this has huge implications. It tells us how galaxies form and evolve. Maybe these galaxies existed in the early universe, but they faded away to nothing. Maybe our theories are wrong and there's simply not as many of these objects as we think they are, or maybe they are hiding in unexplored regions. Maybe they're spread out over such a large area of sky that we just simply can't observe them with our telescopes. Actually, counting these galaxies is fundamental to all of cosmology.
Wow, amazing that we have such a fundamental problem.
Yes, it is starting to get solved.
Do you think that it's possible to observe these phenomena with current or upcoming telescopes?
So the thing is, these galaxies are really hard to observe. Let's think about observing the night sky. Essentially, what the telescope does is it detects photons. These are light particles that hit the telescope. Now, the problem is the Earth's atmosphere, or the night sky itself, is not totally dark. Okay, there's always light coming in some way from every direction. Now, you have to observe for a very, very, very long time in order to get one photon from your dwarf galaxy, whereas you might have 5 or so arrive from just the night sky in general. So the problem is very much it's one of the hardest regions of the sky to observe, basically. Bigger telescopes will help with this. It will shorten the length of time we need to do this.
Nice. So do you have a favorite telescope or one of the coolest telescopes you've ever been to?
Okay, that's a tricky problem. So I really love every observatory I've been to. So I've got a few that sort of stand out. There's the Keck telescope in Hawaii. Hawaii is arguably the best observing sites in the Northern Hemisphere. I should say that there's controversies about us even having telescopes there in the first place. And I think that's an important conversation for astronomers to have. And we need to acknowledge that this is the sacred site for the native Hawaiians. But nevertheless, it does give us one of the most incredible windows on the universe. And just the data you get from that is beautiful. It's just incredible. But probably my favorite place to go observing is the Anglo-Australian telescope at Siding Spring Observatory in Australia. So what you do is you drive from Sydney, and it takes about 8 hours to get there, which is a short drive in Australia, apparently. And you drive up into the Warrumbungles National Park. So you're surrounded by gum trees and rolling hills. And so you have these telescope domes on top of a mountain, and you're surrounded by Australian wildlife. So there's literally kangaroos grazing just outside the telescope, and sort of cockatoos in the trees and emus wandering around. It's just a phenomenal place to be. And I'm biased because I researched dwarf galaxies. In the night sky, you can see the Magellanic Clouds, and these are the brightest dwarf galaxies in sort of our local neighborhood. And you can just see them up in the night sky there, these 2 beautiful satellite galaxies.
That is so cool. And your time in Australia sounds amazing. Thank you so much for being on Physics Chat. It's been really interesting to hear about everything from dwarf galaxies to supermassive black holes.
Okay, great. Thanks for having me.
You're absolutely welcome. Let us know in the comment section, which of the 7 dwarves do you identify with? You know mine, it's Happy, but we would love to hear from you. But for now, from everyone at Field of View, we hope you have an amazing day and goodbye. Bye.
Bye.
No galaxy is the same. I think that's very important to say.